Hello and welcome to my presentation. I am Bahar Asgari from Georgia Tech. In this presentation, I introduce Ascella, an accelerator that executes sparse problems by enabling extreme accesses to memory. Sparse matrices are the main data structure in many applications, such as in the inference of neural networks, in which the weight matrix is sparse, in graph analytics, in which the adjacency matrix of a graph is sparse, and in solving differential equations, in which the coefficient matrices are sparse. The main operation in all these applications is a sparse matrix vector multiplication, or SpMV, which is also the main focus of this work. Since SpMV is a parallelizable operation, an ideal hardware accelerator should be able to execute SpMV by streaming data from memory and applying dot products on data. In such an ideal hardware, we want the data transfer time and computation time to be equal for all blocks of data. As the timeline in this slide shows, transferring data blocks A, B, C, and D takes the same amount of time as their computations do. However, not always we can achieve the ideal case. Since the target matrices are very sparse, they are often stored and transferred in compressed formats. Two well-known compression formats are CSR and BCSR. To process the compressed data, we need to first decompress them. But the challenge is that decompression is slow and can cause a performance bottleneck. Therefore, as the timeline shows, computations for each block usually takes longer than data transfer times, which prevents achieving an ideal streaming. Let's first see why decompression is slow. The frequently used CSR and BCSR formats use three vectors to represent a sparse matrix. First, row indices that indicates the number of non-zero elements or non-zero blocks in a row. Second, the column indices that saves the column index for each non-zero value. And third, the non-zero values that are stored sequentially. Because of such compression mechanisms, if we want to decompress a non-zero row, we need to first read one element of row indices, and based on that, we can read column indices and values accordingly. To clarify, let's see the steps of decompression of CSR for the sparse matrix A shown in the left, that's represented by the row indices, column indices, and values as shown in the middle top. We assume that we can store the three vectors in three BRAM blocks B0, B1, and B2. To start, we read the first element of row indices from BRAM block 0. Then we calculate the number of non-zero values in the first row of the matrix, which is 2. After that, we need to read two elements from column indices and two elements from values. Since they are stored in two different BRAM blocks, and by assuming that we can read only one value from a block at a cycle, we first read 0 and 3 from blocks 1 and 2. Then, in cycle 3, we read the next elements of column indices and values. We continue the same process and read one element from row indices and calculate the number of non-zeros. Here we realize that there is nothing in the second row, so we proceed to the next one. By iteratively applying the same steps, we see that decompressing our example 4x4 sparse matrix in CSR format takes 14 cycles. The decompression for BCSR format is similar. In this example, we assume that instead of individual non-zero elements, we save non-zero blocks of size 2 times 2. The BCSR format saves one row index and one column index per each 2 times 2 block, and sequentially stores the values corresponding to each block as the orange line indicates. To be able to read one 2 times 2 block in one cycle, we distribute the elements of such blocks in 4 BRAM blocks, B2 to B5. Similar to CSR, we start with reading one element of row indices to see how many blocks we are going to read next. there is only one block in the first row. So in the next cycle, we read the column index and the values corresponding to that block. We continue and come up with two blocks in the next row. Since we cannot read more than one block per cycle, we read the first block in cycle 5 and the second block in cycle 6. As we have seen in the simple examples for CSR and BCSR, creating each row of data has two overheads. First, one additional access to the metadata is required to read the row index. And second, one additional computation is required to calculate the number of reads. Besides, we have seen that accesses to data for reading column indices and values are sequential because those accesses are not deterministic. Therefore, we cannot partition them in a way that we can guarantee parallel accesses. To address the challenge, we propose Ascella that avoids such extra accesses to metadata and provides deterministic parallel accesses to data. Ascella enables ideal streaming for sparse problems. As a result of such features, Ascella sustains a balance between the computation and data transfer time. Ascella makes two main contributions. First, it uses a compressed format similar to lists of lists, or LIL. As the figure shows, we store one list per column with each entry containing the values and row indices. Second, Ascella implements the decompression mechanism in a lightweight microarchitecture that connects the memory streamlines to the parallel dot product engine. First, let's look at the decompression mechanism of Ascella. Here we have the same example, the decompression of which from CSR and BCSR formats took 14 and 7 cycles respectively. In Ascella, we know that at each cycle we are going to read one element from each column of the matrix. As a result, we map the column of row indices and values to different BRAM blocks. To start, we read one element from each block and process them. Later slides will show how we process. Based on the process, we go one step forward and again read from all BRAM blocks. We continue doing that until we decompress the sparse matrix A completely. This slide shows the microarchitecture of Ascella. We use read indices to read row indices from BRAM. Then, based on the minimum row index, we create a binary mask. The mask is used to read the values from BRAM to create a dense row and to update read indices for next step. Here we show a numerical example of creating first row, third row, and the last row of the sparse matrix A. We evaluate Ascella by executing SpMV on a group of matrices from SuiteSparse collection. We implement Ascella and the baselines using Vivado HLS on a ZYNQ FPGA. We compare latency and resource utilizations. Ascella and the baselines use AXI stream interfaces to connect to a DDR3 memory. Their frequency is set to 100 MHz and all operations are on 32-bit integers. First, we compare latency for streaming and processing a sequence of blocks for one dataset. These three diagrams show the latency of memory accesses in orange and computation latency in black. As the diagram in bottom and middle show, for both CSR and BCSR, data transfer is fast, but computation creates the bottleneck. On the other hand, the two lines are almost matched for Ascella, which indicate the balanced stream mechanism. Moreover, Ascella reduces the maximum latency of streaming a block to 800 nanoseconds, because unlike CSR and BCSR, Ascella does not transfer the extra row indices for zero rows that occur frequently. We also compare the total latency for different datasets. The total latency at each time step is defined by the maximum of processing time for the previous block and the streaming time for the current block. The diagram in this slide shows the latency normalized to CSR. The x-axis shows the dataset name along with the sparsity of matrices. As it shows, Ascella executes SpMV 2.7 times faster than CSR and about 5 times faster than BCSR. As the diagram in this slide shows, we also evaluate the resource utilization for the target FPGA. The utilization of BRAM is defined by the required memory to buffer data and metadata for one block of size 8 times 8. CSR requires vectors of size 8, 64, and 64 for buffering row indices, column indices, and values respectively. BCSR requires vectors of half size for row and column indices and the same size vector for values. Since we partition and map the values to different BRAM blocks, the tool allocates more blocks for values and one for each of the row and column indices, even though each of the blocks are not fully utilized. Ascella requires two vectors of size 64 to buffer indices and values, both of which are partitioned and allocated to different BRAM blocks. Since CSR does not implement any parallelism, it utilizes the lowest BRAM blocks, flip-flops, and lookup tables. In this presentation, I introduced Ascella, a streaming accelerator for sparse problems. We saw how Ascella streams data from memory and processes them as a stream. Last but not least, Ascella is a significant step towards accelerating larger sparse problems because its storage format facilitates partitioning large matrices and is supported in Python libraries, which makes the full stack implementation more straightforward.